Over the past several days, astronomers across different observatories have noticed something quietly unsettling about Interstellar Object 3, I Atlas. Its coma has begun to shift away from the familiar green glow and take on a distinctly golden hue, a color rarely associated with comets, and even more unusual for an object that did not originate in our solar system. In most cometary observations, green emissions are expected. They are typically produced by excited molecular carbon and related compounds reacting under solar radiation. Gold, however, tells a very different story. It suggests that the light is no longer dominated purely by gas emission, but is increasingly shaped by dust particles scattering sunlight across a broader and warmer spectrum. What makes this transition especially puzzling is its timing. The color shift did not occur as 3I Atlas was approaching the Sun at peak heating, but after perihelion, when its distance from the Sun was already increasing. In classical comet behavior, activity usually weakens after perihelion rather than changing its physical character altogether. This is not an isolated report. Independent observations using different instruments, filters, and processing methods have revealed the same trend. That consistency makes it increasingly difficult to dismiss the golden coloration as an artifact of imaging techniques or observer bias. Something real appears to be changing in the physical state of the object itself. If the gold glow is genuine, it may represent the first visible sign that 3I Atlas is entering a new evolutionary phase within our solar system. One that challenges the simple gas-driven models often used to explain cometary behavior. If this is not an observational error, then what exactly is this golden light telling us about the physical condition of 3I Atlas right now? The changing colors of 3I Atlas are not random fluctuations. Taken together, they form a sequence that reads more like stages of evolution than simple surface activity. From the moment it was first detected, the object has displayed 3 distinct color phases, each pointing to a different dominant physical process at work. The earliest observations showed a deep reddish tone. This kind of coloration is commonly associated with organic rich dust that has been exposed to radiation for extremely long periods. In interstellar space, cosmic rays and ultraviolet radiation slowly darken complex carbon-based materials, producing the red and brown hues seen on heavily processed surfaces. The presence of this color suggests that 3I Atlas spent a long time outside any planetary system. Its surface chemically aged by the harsh interstellar environment. As the object moved deeper into the solar system, that red tone gave way to a green glow. Sometimes with hints of blue, this shift marks a fundamental change. Green and blue emissions are typically linked to excited gas molecules, especially molecular carbon known as C2, along with cyanogen. These species fluoresce when energized by sunlight and the solar wind, signaling that volatile materials were suddenly being released in significant quantities. At this stage, gas dominated the coma, masking much of the underlying dust. Now, in its most recent phase, 3I Atlas appears to be glowing gold. This color indicates yet another transition. Gold tones emerge when dust begins to outweigh gas as the primary contributor to the observed light. As the most volatile compounds are depleted, solid particles increasingly scatter sunlight directly, producing a warmer and broader spectrum. The coma is no longer driven by fresh gas release, but by the lingering physical debris of earlier activity. What makes this sequence remarkable is how clearly separated these phases appear. Typical solar system comets often show overlapping behaviors, with gas and dust emissions rising and falling together. 3. I Atlas instead behaves like an object with a layered history, responding in stages as different reservoirs of material are exposed and exhausted. Such a progression points toward a complex thermal past, one shaped by environments far more extreme and varied than those experienced by ordinary comets native to our solar system. So, what kind of history could imprint an object with such a distinct and orderly sequence of color transformations, long before it ever encountered our sun? One of the most compelling explanations for the unusual behavior of 3I Atlas lies in the possibility that it was not always a quiet interstellar wanderer. Spectroscopic clues suggest that, long before entering our solar system, this object may have spent a significant part of its life orbiting its original host star, not just once, but repeatedly, on a short period trajectory that brought it close enough to be heated over and over again. Repeated passages near a star would have profound consequences. Each close approach would strip away volatile ices, driving off the most fragile compounds and gradually transforming the surface. Over time, what remains is no longer a pristine icy body, but a nucleus increasingly dominated by dust, minerals, and thermally altered material. This kind of processing is consistent with an object that appears chemically selective and structurally resilient, yet oddly depleted in easily sublimated substances. At some point, gravitational interactions within its original system likely destabilized its orbit. A close encounter with a massive planet or a resonant interaction could have been enough to eject 3I Atlas entirely, sending it drifting into interstellar space. There, far from any star, it would have cooled rapidly, preserving whatever layered structure remained after its intense thermal past. For millions of years, it would have traveled through darkness, chemically inert but physically intact. This history offers a natural explanation for one of the most striking aspects of its current behavior. When 3I Atlas entered our solar system, it did not require deep heating to become active. Even a relatively modest increase in solar energy was enough to trigger a rapid awakening. That response suggests a surface already primed by earlier heating, covered by only a thin insulating layer rather than a thick mantle of pristine ice. If this object truly lost much of its original volatile inventory long ago, then its sudden activity raises a deeper question. Where are the gases and chemical species we observe today actually coming from? If not from a well-preserved primordial core, interstellar space may appear empty, but it is far from a true vacuum. Between the stars exists a diffuse mixture of dust grains, gas molecules, and the debris left behind by stellar winds and ancient supernova explosions over vast spans of time. This material slowly drifts, carrying the chemical fingerprints of countless stellar deaths and births. As 3I Atlas wandered through this environment for millions of years, it would not have remained chemically isolated. Even at extremely low densities, continuous exposure allows material to accumulate. A thin coating of interstellar dust and frozen molecules could gradually settle onto its surface, forming a fragile, uneven layer composed of substances that did not originate in its parent star system. This borrowed material would behave very differently once the object encountered a star again. Upon entering the inner regions of our solar system, even modest solar heating would be enough to destabilize this surface layer. Volatile compounds trapped within it could sublimate rapidly, producing a sudden burst of activity that appears intense but lacks long-term endurance. Such a process naturally explains why 3I Atlas seemed to awaken so quickly and then begin to fade just as fast. Instead of tapping into a deep internal reservoir of pristine ice, it may have been shedding a temporary skin accumulated during its interstellar journey. Once that layer was exhausted, the object transitioned toward a quieter, dust-dominated state rather than sustaining prolonged gas-driven activity. If this interpretation is correct, then the unusual chemistry observed in the coma may not reflect the original composition of 3I Atlas at all, but rather the remnants of material gathered between the stars. Could this thin layer of borrowed interstellar matter be responsible for the strange chemical signals that emerged next? One of the most challenging signals detected from 3I Atlas does not come from its motion or brightness, but from its chemistry. Spectroscopic observations reveal a strong presence of nickel in the coma, while iron appears to be largely absent. At first glance, this imbalance seems counterintuitive. Since iron is generally more abundant than nickel in rocky material throughout planetary systems, this does not mean that 3I Atlas lacks iron in its interior. Instead, it points toward a selective chemical process governing which elements are able to escape the surface and enter the coma. What we are observing is not the bulk composition of the nucleus, but the fraction of material that can be mobilized under relatively gentle heating and solar radiation. A key clue lies in the behavior of metal carbonyl compounds. Nickel carbonyl is chemically more stable and more volatile than iron carbonyl under comparable conditions. This difference allows nickel-bearing compounds to sublimate and migrate into the coma more efficiently, while iron-bearing compounds are more likely to break apart, react, or remain trapped closer to the surface. As solar radiation dissociates these compounds, free nickel atoms become visible in spectroscopic data, creating a pronounced signal without a matching iron counterpart. Such selective metal emission is extremely rare. Only a handful of comets have shown comparable behavior. And even then, the signals were far weaker and more transient. The clarity of the nickel signature in 3I Atlas suggests an unusual chemical environment, one shaped by both its past thermal history and the specific materials available near its surface. If this chemical mechanism is indeed operating as observed, it implies that the evolution of 3I Atlas is being guided not only by temperature and distance from the Sun, but by subtle differences in molecular stability that determine which elements are released and when. How might this chemically driven selectivity influence the changing colours we see today? And what does it reveal about the current evolutionary path of 3I Atlas? After perihelion, the energy environment around 3I Atlas began to change in a decisive way. Although the object was still relatively close to the Sun, the most volatile compounds near its surface had already been exposed to intense heating. As a result, these easily sublimated materials were depleted rapidly, leaving behind substances that respond more slowly to solar energy. As the gas supply diminished, the coma gradually shifted toward a dust-dominated state. Solid particles released earlier continued to linger and scatter sunlight directly, producing a warmer spectrum that appears yellow to golden rather than green. This transition reflects a fundamental change in the driving force behind the observed light, from molecular emission to physical reflection. The organic compounds that once contributed to darker red tones were not immune to this process. As the surface continued to erode, many of these materials were carried away along with the dust, smoothing the spectral profile and reducing the contrast seen during earlier phases. The result is a more uniform, muted glow that signals exhaustion rather than renewal. Such behavior is characteristic of an object approaching the end of its most active phase. Without a deep reservoir of fresh volatiles to replenish the coma, activity becomes increasingly governed by residual debris rather than ongoing chemical release. In this state, brightness may persist temporarily, but it no longer reflects vigorous internal processes. This golden phase, then, may not represent stability at all. It could instead be a transitional moment, marking the point at which 3I Atlas shifts from energetic transformation towards structural vulnerability. Is this quiet fading simply the natural conclusion of its activity? Or could it be the prelude to a far more dramatic change? There is reason for astronomers to treat this golden phase with careful attention, because it is not without precedent. In a small number of past cases, comets that transition toward warmer, dust-dominated colors were later observed to fragment, sometimes abruptly. While color alone does not cause breakup, it can signal underlying physical stress within the nucleus, as volatile materials are lost. An object also loses an important form of structural support. Sublimating gases help relieve internal pressure and redistribute stress across the surface. Once those gases diminish, the remaining structure must bear thermal and mechanical forces more directly. Cracks, weak layers, and internal fractures that were once stabilized can begin to propagate. For 3I Atlas, this vulnerability may be especially relevant. The object is now moving deeper into a region of the solar system dominated by strong gravitational interactions. Its future path brings it closer to Jupiter, a planet whose immense gravity has reshaped, captured, and destroyed countless small bodies over cosmic time. Even without a direct encounter, tidal forces and orbital perturbations can amplify existing weaknesses. This does not mean that fragmentation is inevitable. Many objects survive similar conditions without catastrophic failure. However, the combination of a dust-dominated coma, a history of thermal processing, and an approaching gravitational giant places 3I Atlas in a category that warrants close monitoring rather than complacent assumptions. If changes are coming, the signals may already be subtle and easy to miss. The current moment could represent a narrow window in which the object is still largely intact. yet already transitioning toward a less stable state. Could this be our final opportunity to observe 3I Atlas as a coherent body before its physical story takes an irreversible turn? The close passage of 3I Atlas near Earth is more than a convenient observing opportunity. It is a rare alignment in time, one that allows professional observatories and dedicated amateur astronomers alike to study material that did not originate here. For a brief moment, an object shaped by another star system has entered our reach, carrying information no spacecraft could yet retrieve. Every spectrum captured and every image recorded adds to something far larger than this single object. For the first time, we can directly compare interstellar material with the familiar building blocks of our own solar system, testing whether the processes that shaped our planetary neighborhood are universal or merely local accidents of history. In that comparison lies the potential to refine, or even rewrite, how we understand planetary formation across the galaxy. 3I Atlas also serves as a quiet reminder of scale. It is not a visitor with intent or meaning, but a fragment of another cosmic story, one that began around a distant star long before Earth existed. Its journey through interstellar space connects events separated by millions of years and unimaginable distances, collapsing them into a single observable moment. Science reaches its greatest strength not when it claims certainty, but when it recognizes the limits of its knowledge. Objects like 3I Atlas force us to confront how much remains unknown, and how fragile our assumptions can be when exposed to evidence from beyond our familiar environment. They do not offer simple answers, only sharper questions. If a small, silent body like 3I Atlas can challenge our understanding of chemistry, evolution, and cosmic history so profoundly, then how many other interstellar travelers are still passing unseen, carrying stories we have not yet learned how to read?